Welcome Year 11s to the start of a brand new topic, transformations. When speaking to my colleagues who have taught maths methods before, they tell me that the two topics that students find the most difficult in Year 11 are transformations and circular functions. This topic is drawn on heavily in Year 12, so I strongly recommend that you take the time to work through this material very carefully, ask lots of questions, and stay up to date with the exercises. In this video, I'm going to cover 3 basic transformations. These are the only transformations you need in this course, and you've already heard of them in your Year 10 studies at school. They are a translation, which is like shifting, a reflection, which is like a mirror image, and a dilation, which is like a stretch. Now, these words, shift, mirror image, and stretch, that's everyday language. And when I've taught transformations to a Year 7 class who's not doing methods, just understanding what these things do, the language of shifting without changing the orientation, which would be a rotation, mirror image and stretch, they understand that. In this course, we're going to make these terms very precise and we're going to give mathematical definitions. I want you to pay attention to these definitions, and quite frankly, I think you need to know them by heart. So, in the first few pages of this handout, I'm going to spend a lot of time developing the theory because I think it's important for your understanding of this topic. I know we want to do questions, but before we get to those questions, I want to make sure that you have a good understanding of these terms so that you can tackle the more difficult questions. So let's start. What's a transformation? Before that, I'm going to define a symbol, r squared. Now, the symbol r refers to the real numbers. R squared is like a combination of 2 real numbers. So you could think of this in words as the set of all coordinates. The technical term is ordered pairs with 2 real numbers. So every element of this set lies in the Cartesian plane. Every point on the xy plane lies in r squared. So, what's a transformation? If you look at this equation here, you'll see that this is written a lot like a function. And that's because it is. A transformation is a kind of function. That's so important that I'm going to write it down. Now, you'll remember that the set written on the left is called the domain, and a set on the right is the codomain, which contains the range. So, the input and output of a transformation is a coordinate. Before, our functions acted on one number. A transformation, on the other hand, is going to act on 2 numbers, x and y. And what's it going to do? It's going to take a coordinate xy, and it's going to output another coordinate x prime, y prime. You can think of xy as the old coordinate before the transformation has taken place, and x prime, y prime as the new coordinate. Now, what's going to happen is when I write down x prime and y prime here, I will replace x prime and y prime with an algebraic definition in terms of x and y. Now, if that sounds abstract, which it is, let's consider two examples which I think will make this clearer. So, here's our first example. I've got the transformation t, which maps r squared to r squared. And when the transformation acts on the coordinate xy, the output is x plus 5, y minus 3. So, using our notation, I'm going to say my new coordinate, x dash, is x plus 5. And my new y coordinate, y dash, is y minus 3. This question says, find the image of this coordinates negative 2 to 4. The word image just means the coordinate after the transformation. Doesn't have to be a coordinate, could also be a function as well. But we'll stick with coordinate because that's what this question is asking about. So, my new coordinates x dash and y dash are defined in terms of my old coordinates, negative 2, and y equals 4. So, that means if I substitute these two numbers, I get x dash equals negative 2 plus 5, and y dash is 4 minus 3. The image, my new coordinate, is 3, 1. So let's just quickly check. Does this agree with what the transformation defines? I've increased the x value by 5, and I've decreased the decreased the y value by 1. Yes, that matches what we've got here. Okay, hopefully that made sense. If not, just send me messages on Teams and I'll get back to you. I know it's abstract. The reason why I'm using this notation of x dash and y dash is because we're going to need it later in this topic. There is a method to the madness. Every time I decide to do something in this class, I have a reason for it. It's actually not to make you miserable. It's actually to make your life easier. All right, let's go on to our next example. Now, this time, I have given you the image. And I want to find the input, or the pre-image. And you'll notice our definition for the transformation is a little bit more complicated. This time, my new coordinate is 2x plus 4. And my new coordinates after the transformation is 3y minus 2. However, this time, the transformation gives me an output of 10 for x and 14 for y. And now I'm asking the question, what was the original coordinate that got me to an output of 10 and 14? Okay, slightly different question. In this question, we're told the new coordinate after the transformation, and we want to work backwards. So now what I need to do is solve for the original coordinates, x and y. Okay, and at this point, the math is relatively straightforward. Okay, so x equals 3 and y equals 16 over 3. And so that means my old coordinate, the question doesn't ask for it, but the pre-image of 10, 14 is 3, 16 on 3. But if you stop here, you're fine. All right, key idea. X, y is my old coordinate before the transformation. X dash, y dash is my new coordinate after the transformation. And example 1, we went forwards. Example 2, we went backwards. Okay, so now you've got an algebraic understanding of what a transformation looks like. It's like a function. I can go forwards and backwards. Now what I want to do is take this notation and define the three transformations: translations, reflections, and dilations. So turn the page. Go to one more page of quick theory, and then we're about to get into it. So, I mean, you can read this. So I'm going to go through this relatively quickly. The main idea I want to get across to you is when I have the two coordinates x, y, and x dash, y dash, they are actually measured along the same axes. So imagine a situation where, let's say I have the origin 0, 0. I apply some transformation. Maybe it's moving 4 units to the right. And my new coordinate is x dash, y dash. I want you to add these two to the diagram, please, in your notes. The main thing I want you to understand is the x and y axis, which was used to define the first point xy, is the same axis used to define the coordinates for x dash and y dash. So, although I moved the point, I did not move the xy plane. Okay? The axes stay in the same position. Now, the reason why I need to say this is because I get confused because I've gone to uni and I've done something different where I actually move the axis. And that's not the interpretation that we're doing in this course. Here we're saying keep the points, you move the points, but you keep the axis in the same position. And later, if you take more studies in maths or physics or engineering, you might actually keep the point in the same position and move the axes. And that's relevant to things like computer vision and so on. So, key point here, the axes did not move. And one of the things that I don't like about this notation is that the letters x and y have been used 3 different ways in this diagram. First, it was used for the starting point, then for the new point after the transformation, and this x and this y refers to a coordinate system where I define an x-axis, a y-axis, and an origin. This one doesn't change. A transformation for our purposes moves one point to a new point within the same set of axes. Sorry to belabor the points, but you'll see what I mean when I go to example 4 now. So imagine a situation now where I have the graph in blue, y equals x squared. And now I undertake a transformation where I translate the graph 4 units to the right. Now you've already done a unit on parabolas, so you know the equation of this graph in orange after the transformation is y equals x minus 4 squared. Now, when we do our calculations, we will say if x dash y dash is a coordinate on the transformed graph, then we wouldn't write y equals x minus 4 squared for these two symbols. We would actually write y dash equals x dash minus 4 squared. You see why this might be confusing? It's because I'm using x and y in different ways. I'm just going to change the color here. Now, what you'll notice when you read the book is they'll do this calculation to find the new rule after changing x, y to x dash, y dash, and you get a rule like this. And then in the last line, they drop the dashes. And so we would say two statements. These two statements are the same in purple. First, y dash equals x dash minus 4 squared. And then they say the equation of the image, which is a transformed graph, is y equals x minus 4 squared. So a question that students will ask, which I can imagine you asking, is why can I drop the dashes here? And the reason why we are allowed to drop the dashes is because in this statement here, we are no longer referring to x dash y dash. We are instead referring to the xy plane, which didn't change. Okay? So, because the coordinates xy and x dash y dash are defined with respect to the same axes, which I've done in green there, x and y, you can drop the dashes because if you refer to an x value and y value according to these axes, they follow this rule. Okay? If I was in class, I would ask if you had any questions because I can imagine some confused faces. If you're not happy with that, just park it for now. Feel free to ask me when I'm in class or just send me a message on Teams. Hopefully, this isn't controversial. Maybe the dropping of the dashes is, but I hope that you're happy to say that this parabola in orange has the equation y equals x minus 4 squared. If you're happy with that, what's going to happen in this topic is we'll do the calculation with the dashes and then we'll just drop them and move on. Okay? I took a few minutes to try to explain why we were allowed to drop the dashes, and this is my reason here. I'll say coordinates in the xy plane. Okay, I've had enough of that. Let's move on. So, let's define some transformations. Our first transformation is called a translation. So, in this course, we consider a movement horizontally and vertically. Now the diagrams aren't super important, but I'm just drawing these to give you a sense of what's happening here. So if h is positive, the transformation is to the right. And if k is positive, This should say y-axis. Please make that change, everybody. Positive direction of the y-axis. And if I change y to y plus k, it's upwards if k is positive. Okay. Now on the last page, I'm going to give you all these results in a table. I hope that as you're reading this makes sense. I'm replacing x with x plus h to increase the x value if it's going to the right, and I'm replacing y with y plus k to move the point upwards if k is positive. Okay, now, if you're happy with that, I want to prove the following result. Suppose I have the graph y equals f of x. I translated h units to the right and k units up. My claim is if I start with y equals f of x, then the image after this is y equals f of x minus h plus k. You have used this result for almost 2 years in your work on parabolas. For example, turning point form is x minus h squared plus k, and you can include an a term out the front if you want. Now, I claim that this generalizes to any function. Doesn't have to be a quadratic, doesn't have to be a polynomial. If I replace f of x with f of x minus h plus k, that corresponds to these two translations. So this is a very powerful result. Now, why is this true? Using just the notation that we've introduced on this page, we can actually prove this. So, let's start by defining my transformations. My new x-coordinate is x plus h, and my new y-coordinate is y plus k. Now, we also know that y equals f of x. True? That's what we know. Now, here's the next step. What I'm going to do is rearrange for x and y. We have the following results. X equals x dash minus h, and y equals y dash minus k. Now you might ask, why am I doing this? Well, what I'm doing is I'm solving for the old x and y coordinates in terms of the new x and y coordinates. Because if I do this, I can now take these two expressions and substitute them into my original equation. And watch what happens. If I substitute these into y equals f of x, we get an equation which defines the new y-coordinate in terms of the new x-coordinate. Alright, I can rewrite this as y dash equals f of x dash minus h plus k. And you'll notice I've pretty much got the result that I want. I just need to drop the dashes. And I'm happy for you to just write at this point the equation of the image is y equals f of x minus h plus k. Alright, why am I allowed to drop the dashes? Either because Mr. Chu said so, or because of that ramble from a few minutes ago. Whichever one you like. Alright, so I've proved this now for any function, not just for the parabola. Now, you can now remember this result, but the process by which we got to this result is going to be very, very useful because we're going to do this for other transformations later in this chapter. So if you're unclear about what we did here, please get in touch with me and I'm happy to explain it to you. Alright, next transformation is the reflection. So again, I'm going to draw some pictures for you. Suppose I have the point x comma y. If I reflect about the x-axis, that's the horizontal line here, acting as my mirror. And what I want you to remember is if I reflect about the x-axis, the x value stays the same, and the y value is flipped. It's a little bit easy to get this confused. So I reflected about the x-axis, but I didn't change the x value, I changed the y value. Same thing with a reflection about the y-axis. This time, my image is obtained by a reflection about the vertical line, the y-axis, and my new coordinate is now negative x. So this time, if I reflect about the y-axis, x is flipped, and y stays the same. Alright, there's a couple of results. Because I don't want this video to take too long, I'm going to leave these two results for you to prove as homework. Should only take you about 4 or 5 lines. If it takes much longer than that, you're doing it wrong. Alright, but we get two really nice results. If I reflect about the y-axis, if I reflect about the x-axis, y equals f of x changes to y equals a negative f of x. And if I reflect about the y-axis, I get f of negative x. So the first thing you'll want to do is define x dash and y dash. And then substitute these, well, you'll need to solve for x and y, and then substitute your expressions into y equals f of x. Alright, so here's a skeleton. Alright, that's all you need to do. So I'm going to leave that with you. The completed handout will be available to you on OneNote, and you'll be able to check your answers. Alright, next one, dilations. So, this time, I need to draw more than one picture, because if I don't, it may look like a translation. So, suppose that I have the points x1, y1 and x2, y2. And let's imagine, just for sake of argument, that I choose a factor of 2. Now, what this does is, again, you need to notice, I'm dilating away from the x-axis. So here I've doubled the y value, and here I've doubled the y value as well. Notice x stays the same, and y changes. Okay, here I've chosen a to be positive, and maybe a equals 2, just for example. Okay, notice that this gap is smaller than this vertical gap here. That's what's supposed to happen with a dilation. Alright, that's a dilation from the x-axis, and it causes the y value to change. Similarly, I can dilate by a factor of b from the y-axis, and what this does is, this causes x to change, whereas y stays the same. All right, we'll draw another picture. Okay, let's say I do this like times 8. If this is about double this, then this point here should be about double this distance from the y-axis. So bx1, y1, and then this point here is bx2, y2. Okay, the y values have stayed the same, the x values have changed. And in this example, b is positive, and maybe, I don't know, b is like about 8. Now, I want to make one comment here. The Cambridge text uses A and B in the opposite way to the way I do in the notes. And it's really annoying. I think it makes more sense to make this choice because of turning point form. In turning point form, we write a bracket x minus h squared. So if we use the letter A here, we get that turning point form. So that's why I've chosen to go a different row to the textbook. It doesn't really matter what letter you use. What you do need to know is that if you change the y value, you are dilating from the x-axis. Okay? All right. So a couple of results as well. I'm going to leave this one for homework. I would need you to define x dash and y dash, solve for x and y, and then substitute into y equals f of x. Now, this one, there's one result that is surprising. So I'm actually going to do this one. Suppose I take the graph y equals f of x, and I dilate it by a factor of b from the y-axis. I don't get f of bx. I actually get f of x divided by b. So let's see why this happens. Okay, this is really important because it's a common mistake that students make. So if I dilate by a factor of b from the y-axis, my x value is now b times x, and my y value hasn't changed. So if I rearrange for x and y, I get x equals x dash divided by b, and y equals y dash. Let's now substitute this into y equals f of x. What I get is y dash equals f of x dash divided by b. And you see what happened here? If I drop the dashes, the equation of the image is y equals f of x divided by b. Alright, so x over b, not b times x, if you dilate by a factor of b from the y-axis. Okay, so here's a summary. I think you need to have this table memorized, personally. And for most of the work that we do in this chapter, knowing this column is going to be really useful. In the next exercise, in the next lesson, what we're going to do is we're going to combine more than one transformation. And if we do that, it's going to be helpful to know the mapping notation. So for easy work, knowing the function notation is going to be really helpful. For more difficult work, knowing the mapping notation is going to be essential. So I want you to know both. I've got 2 more examples to show you after this page. I'm going to show you both methods. But what the emphasis of this lesson is on the mapping notation. So that's today's focus. And the function notation is nice to remember for what I'll call routine questions that you see a lot in textbooks. All right, so please make sure that you are either understanding or able to recall this table either through memorization or writing down the mapping notation each time. So, a couple of comments before we dive into our final examples. There are different ways to describe translations and dilations. So, we've already said the first one. Now, positive direction is unambiguous. If I say to the right, that's fine, but you need to tell me that h is positive. It doesn't really make sense to translate -3 units to the right. Like, we know what that means, but please just say 3 units left instead to avoid confusion. Now, another way to specify a translation is parallel to the x-axis. Now here, I haven't said positive direction because the x-axis has a convention where values to the right are increasing. So if you just say translated 3 units parallel to the x-axis, it's assumed that you are translating in the positive direction. Personally, I would just use these two and don't use the third one because it's not as precise. Now, same thing for dilations. I can dilate by a factor of a from the x-axis, but notice this wording here. I can also dilate parallel to the y-axis. And what this is saying is, my dilation is causing my y values to increase. So the first statement emphasizes the fact that we are dilating away from the x-axis. And the second statement is emphasizing that we're dilating in the y direction. All right, so parallel to the y-axis is not the same as dilating away from the x-axis. Now, the reason why I'm mentioning this is because you'll see a mixture of terminology used in the Year 12 exams. So just want to highlight that to you now, because it's going to make your life easier when you see this come up. The standard terminology that's most commonly used in textbooks is the first ones. But occasionally, you'll see other ones used in the exams as well. All right, let's conclude with 2 examples with an emphasis on mapping notation with the dashes, but I'll show you function notation as well. So, example 5. Here's a graph, y equals x minus 2 all cubed plus 4. What am I going to do? I'm going to move it 10 units to the left. So that means I am moving it in the negative direction of the x-axis. That's going to cause the x values to decrease. So first I will rearrange for x and y in terms of x dash and y dash. And I'm going to substitute this into the equation that was given. So wherever I see y, I'll write y dash. Wherever I see x, I'll write x dash plus 10. Simplify. And that means the equation of the image is y equals x plus 8 all cubed plus 4. Now, that's method number 1, using what's called mapping notation, the x dash and the y dash. Here's the second method. The second method states, suppose that my graph is f of x. If I translate 10 units to the left, that's f of x plus 10. So if h is positive, f of x minus h is a translation to the right. So choosing negative 10, I replace x minus negative 10 with x plus 10. This equals x minus 10, x plus 10 minus 2 cubed plus 4, which equals x plus 8 cubed plus 4. And so again, the equation of the image is y equals x plus 8 all cubed plus 4. Now I know what you're thinking. Mr. Chu, surely we go with the purple writing because it's quicker. And my response is, for the first exercise, that's fine, but I want you to know the blue method as well. You won't be able to do all of the work with just the function approach. Sometimes it's going to be easier, and I mean significantly easier, to use the x dash y dash method. And for a different kind of problem that's not as easy as this, you basically make life much harder for yourself if you don't use the x dash y dash method. So for your own development, I actually recommend that you use the blue method for this exercise. But if you're pressed for time, I will not protest if you use the function method, but just be aware that if you don't do this hard work now, you will have to do it later. And this is going to come back again in year 12. So this is the best time to lay a good foundation for success next year. All right, let's do one more example. Same graph. This time we're dilating by a factor of 5 from the x-axis. So we want to find the image. If I dilate from the x-axis, the x-coordinate doesn't change. My y-coordinate is multiplied by 5. So rearranging for my old coordinates in terms of my u-coordinates, y equals y dash divided by 5. If I substitute this into the equation, y equals x minus 2 all cubed plus 4, I get y dash divided by 5 equals x dash minus 2 all cubed plus 4. And to get y dash on its own, I multiply everything by 5. So I multiply the bracket by 5, and don't forget to multiply the 4 by 5. It's a very common mistake, and it's a mistake that I made when I was doing things in a rush. If you do something to one side of the equation, you need to do it to the other side. So if you multiply by 5, you've got to multiply everything by 5 if you are adding terms together. And don't forget to answer the question. The equation of the image is going to be specified in terms of x and y. So it's going to be y equals 5, x minus 2 all cubed plus 20. All right, so that's the method of images, or using mapping notation. Now let's solve this question again using function notation. So if my function is f of x, a dilation by a factor of 5 from the x-axis is 5 times f of x. So that means I multiply everything by 5. Okay, and I'm making this really clear with this big square bracket. Everything is getting multiplied by 5. Okay. And then the equation of the image is y equals 5x minus 2 cubed plus 20. If you can do this last page, you are ready to do the 2 exercises. If I lost you with the theory, I think that's okay. It's going to take a bit of time, but if you're really confused at this point, please just get in touch over Teams, and happy to chat with you about this. There is a reason why transformations is found to be difficult by most students, and that's because it's a pretty abstract topic, and all these dashes floating around don't help. So you need a lot of practice. Now, I know that the polynomials test is coming up. Your instinct is going to be to focus on that. However, I'm going to suggest that you take the half an hour to an hour needed to do 7a and 7b, because that's going to set you up really well for our next topic. If you don't do it now, you have to cram it at some other point. And maths isn't a subject that you want to cram. You want to be building your understanding as you go, steadily. So please complete the required questions from the work program from 7a and 7b. I've deliberately kept it light because of your workload for polynomials. I think you should find it's pretty doable. So please take the time to do it, and we will continue the story of transformations when we come back next lesson, when we start combining more than one transformation at a time. I look forward to seeing you then.